remember when we looked at the Hill equation or the Hill plot, what we were able to determine is that when n is greater than or less than 1, then we exhibit either positive or negative cooperativity, respectively. And so what does that mean exactly? So that means that we're having some sort of communication between the between the ligand binding sites. And so if we're looking at heme, for instance, which is a tetramer, and we have our 4 subunits here shown in yellow, if oxygen comes in and binds, then there must be some way for this to communicate to the rest of the protein that O2 is bound here. Otherwise, why would we have this sort of communication between multiple subunits? Why would we be able to increase the affinity for other subunits if O2 is bound to one of the subunits? And so what we need in order for this to happen is we need to have multiple binding sites. So for hemoglobin, we have 4 binding sites. Okay, and so that requirement is checked off. And then they have to be able to interact with each other. So what that means is there need to be some sort of either covalent or non-covalent interaction that allows the subunits to talk to each other, generally at the subunit interfaces, here, and from the ligand binding site through the subunit interface and to the other ligand binding sites. And so we'll discuss in a bit about how that actually happens in hemoglobin. But why doesn't this happen in myoglobin? Because myoglobin also can bind O2, but remember this is a monomer. It doesn't have, doesn't exhibit any quaternary structure. There are no subunit interactions, so we don't see cooperativity in myoglobin. And that's because we don't have these subunit interfaces that we see in hemoglobin. Okay? So this whole phenomenon where either we're ligand binding either increases the affinity of binding a ligand at other binding sites or decreases it is called cooperativity. And so it's an interesting phenomenon because there's no direct connection between these ligand binding sites. In other words, what I'm trying to say is that the hemes where O2 binds don't touch each other. And in fact, the hemes, for instance, between an alpha and a beta subunit are 24 angstroms away. That's roughly the equivalent of 22 carbon-carbon bonds or the size of arachidic acid, which is a 20-carbon chain fatty acid. So these are a really long way, apart from each other, and the hemes don't interact with each other directly. Instead, the interaction is through the peptide backbone via side groups, such as ones that form hydrogen bonds or form other intermolecular forces that allow for this communication through the peptide bonds and then to the other ligand binding sites. So this phenomenon where we can have communication over long distances through the protein is called allostery. And so this is when binding of an effector, for the case of hemoglobin, we're talking about oxygen. That is the effector molecule, where the binding of an effector influences the binding properties at a different binding site. Okay? And we can think about this in terms of cooperativity in 2 different ways. So positive cooperativity, again, in the Hill plot, this is when n is greater than 1. And so that's when the first binding event increases the affinity at the remaining sites for the ligand. If n is less than 1, then we have negative cooperativity. And that's when binding of the ligand, the first binding event, reduces the affinity at the remaining sites. And so for O2 binding, what we see, we exhibit positive cooperativity because when O2 binds to the first site, that increases the affinity of O2 for the other ligand binding sites, for the other O2 binding sites in hemoglobin. Okay. Now, we can also define an effector as a homotropic effector or a heterotropic effector. A homotropic effector is when the effector molecule, again for hemoglobin, O2, is identical to the ligand. So in this case, the ligand, remember, we're defining by the equation of P plus L equals PL. So in this case, the native ligand for hemoglobin is O2. So we go hemoglobin plus O2. All right. So the effector molecule, that is the molecule that causes the change in binding, so the molecule that induces cooperativity, is the same as the ligand. In this case, O2 is both the ligand of hemoglobin and also changes the affinity for O2 at other sites. So O2 in this case is a homotropic effector molecule. Heterotropic is when the ligand and the effector molecule are not the same. So in the we'll talk about this later in class, but 2,3-bisphosphoglycerate is a molecule that can bind to hemoglobin and decrease the affinity for the ligand. That is, it can decrease the affinity for O2. So in this case, BPG is a different molecule than O2. So it's a heterotropic effector, and what's more, binding of BPG to hemoglobin actually causes a decrease in the affinity for O2. So we would call BPG a heterotropic negative effector, and this displays heterotropic negative cooperativity.